Okay, let's consider the definition between for the distance between a point and set, or a distance between a set and a set. So the dxe here, so E is a subset in Rn. So the dxe means the infimum of dxy where y is from E. Okay, so in other words, dxe is you can find a sequence from a sequence of points in E such that they converge to their distance to x converge to the distance between x and E. So that's the distance definition for the distance. And similarly, the distance between two sets is the distance between x and y, infimum of distance between x and y for x and y taken from E1 and E2 respectively. Okay, so that's the definition. There is a trivial example in notes. I will not go over that, but you can take a look to have some feeling of this. So this is just a common understanding of the distance between point sets and set and sets. Okay, so now I'll give a theorem to show that if you have a subset F that is non-empty and closed, so non-empty closed subset F in Rn, and there is a point called x0, then there must be some y in F such that the distance between the point x0 and F is equal to the distance between x0 and this point y. Okay, so that means you must be able to find some, say this is the x0 and this is the F, then you must be able to, it's closed, it means that you must be able to find some point y such that the distance here is equal to the distance between the point x0 and F. Okay, so first of all, if this x0 is inside F, then you just choose your y to be x0, and then the distance will be just 0 here, right? Both sides will be 0. So the interesting part is that the x0 is not in F. It's not in F since F is non-empty, so we know that you can choose a ball centered at x0, and you make this ball sufficiently large, then this ball should overlap with F. Okay, so you have x0 and F is somewhere there, then you make this ball large enough, then you should overlap with this F. Okay, so that means, that's what I'm saying here, there exists some delta which is the radius of the ball. So when the ball is large enough, this closed ball centered at x0 and the delta just overlaps with this F. And note that this F is closed, and this closed ball is also closed. The intersection of the two is still closed. Okay, so the K is still closed. But note that this is bounded, right? It's a bounded ball. So the K is also bounded, since K is just a subset. At the same time, K is closed. So it's a bounded and closed set, so it has to be compact. So K must be compact. Now, let's define a function f. It's from Rn to R. And the definition is very simple. For every point, I just evaluate its distance from x0. So this is just like just x0 minus x absolute value. Okay, and it's easy to check that this function f is continuous. Okay, you can either use the original definition for continuity. For every epsilon, there exists delta such that when the actually you can make it even simpler. You can show that this is a Lipschitz function. So fx. So here the fx minus fy is equal to, as I said, x0 minus x minus x0 minus y. And this is less than triangle inequality is less than this. Okay, so this f is actually Lipschitz continuous. Okay, it's Lipschitz continuous, so it must be continuous as well. And now continue with our proof. Since k is compact, as we showed earlier, we know that you have a continuous function f that is defined. You can restrict f to the k, and f is continuous. K is compact means that f can obtain a minimum value on k. Right? That's the property of continuous functions. If you have a continuous function defined on a compact set, then you can reach the minimum. It has a minimum value over there. So that means there exists some y such that fy, there exists some y in k such that fy is the minimum value of f over k. And now the left hand side is d x naught y, and the right hand side is minimum value of d x naught x, where x is taken over the k. So that means the infimum here is actually the minimum. Okay, and you know that this minimum value over k will be also the minimum value over f, because as we showed earlier, this is the x0, this is the f, and you're making this k, you're making this ball large enough, so these points will be even closer to x0 than the other part of the f. So this is the entire f. So these points will be even closer to x0, right? So the minimum over this area should be also the minimum over the entire area, considering their distance to x0. Okay, so next we'll show a theorem about the distance between a point and any given empty set. So suppose we have a set E in Rn, and the E is non-empty. Then we can define the distance function to E as this f. So for every given point x in Rn, the f of x is the distance between x and the E. Okay, so you see this is the E. So if x is already inside E, then distance will be 0. If x is outside, then the f of x tells you the distance between x and this E. Okay, and we're going to show this f is a uniformly continuous function. Actually, we can show that f is a Lipschitz continuous function. That is a stronger continuity than uniform continuity. Okay, so this is we can actually show that f is actually Lipschitz continuous. So to show that, let's say for any 2 points x and y, and for any epsilon greater than 0, let's focus on y here. For any x epsilon greater than 0, there will be a point z in E such that the distance between y and z is less than the infimum of this dyw plus epsilon, where this w is from E. So what this is saying is that, remember that if I have a E here, and this is my y, and then I know that there will be the distance between y and E is the infimum here, right? This is the definition. And because this is infimum, that means for every epsilon, positive epsilon, there will be some z inside E such that the distance between y and z is is smaller than the actual distance or the infimum plus epsilon, right? That's the property of infimum. Okay, so it's the infimum means that you can, for any epsilon, you can find some value z such that the dyz is smaller, it's definitely bigger than or equal to the infimum on the one side, but it's also smaller than the infimum plus this epsilon. That's the property of infimum. So that's what we just said. Because this y dyz on the one hand, it must be bigger than or equal to the distance between y and E, since this z is just the one element of E. So this will be bigger than or equal to that. But on the other hand, because this, we chose this z such that this happens, this holds. So that's why the dyz, this is a dye, it is also bigger than this minus epsilon. Okay, it's also bigger than that. So now you can see I have this quantity here, and it's in between dyz and dyz minus epsilon. Okay, so for every epsilon, you can find the z. So now you can see I take the difference between dxe and the dye. So dxe must be less than or equal to dxz, because z is one element from E, right? And the dxe is the infimum over all those distances. So that's why this is less than or equal to that. And on the other hand, I know that this is bigger than as we showed here, this is bigger than this. So the negative of this will be smaller than or equal to the negative of this, right? So that's why this is bigger than that. But when you put the negative here, then this negative of this will be less than or equal to the negative on the right hand side. Okay, so that's why this is less than that, and this is less than that. Okay, so I get this inequality here, and now I combine these two, and you have two negatives that becomes plus. Okay, so I have this plus epsilon, and notice that by triangle inequality, dxz minus dyz is less than or equal to dxy. Okay, that's how I get this. And now notice that this epsilon is chosen arbitrarily. So epsilon can be any positive number, and that just means if this is less than or equal to this plus epsilon for any positive epsilon, that just means this left-hand side must be less than or equal to this. Okay, that's why this is less than or equal to this. But notice that by the definition of f, this is just f of x, this is just f of y, so I show that f of x minus f of y is less than or equal to dxy. Okay, and remember that x and y are arbitrarily chosen, so the fy minus f of x is also less than or equal to that. Okay, I can just need to switch the x and y, and I'll get the same one. So that means the absolute value of fx minus f of y will be less than or equal to dxy. So this on the right hand side is just x minus y norm. Okay, now you can see that f is a one Lipschitz continuous function. Okay, it's a continuous function, a Lipschitz continuous function with Lipschitz constant 1, and that implies that the f is a uniformly continuous function. Okay, now let's see a corollary of that. Okay, suppose we have two sets, two non-empty and closed sets in Rn. And suppose at least one of them is bounded. Okay, I need one of them to be bounded. Then there must be one point from f1 and then another point x2 from f2, such that the distance between these 2 points from the two sets separate respectively is equal to the distance between them. So that means you have f1 here, and I have f2 here. Then there will be some point x1 here, and some point x2 here, so that the distance between these 2 points is actually the distance between the two sets. Okay, so we need one of the two sets to be bounded. So suppose without loss of generality, let's say that f1 is bounded. Now the f1 is non-empty, bounded, and closed, so f1 must be compact. Right, here should be compact. Okay, so now I define function f on Rn such that f of x is the distance between any point x to f2. So f1 is the bounded one, f2 is could be the unbounded one. But say this is the f2 that could be unbounded, and I'm defining this f of x as the distance between x and f2, same as the previous one. And remember that the conclusion from the theorem is that the f is uniformly continuous. Okay, we actually just need the continuity, but actually it's uniformly continuous, and also actually it's Lipschitz continuous, but we only need the continuity of f. The reason is once we have that f is continuous, then we know that since f1 is compact, we have a continuous function. When we restrict it to the compact function f1, we know that this f will attain a minimum value over the f1. So let's say that f attains a minimum value at x1. Okay, that means over this f1, I know that the little f function will get to the minimum x1. Okay, but actually this minimum, say this is the f1, this is the f2. So this x1 is somewhere here. Okay, the closest the point closest to f2. Okay, but anyway, we know that since we have a continuous function defined over this f, when we see it as continuous function defined over this space, the entire Rn, and when we restrict it to the f1, which is a compact set, we know that it attains a minimum x1, attains a minimum value at x1. So this is the point x1 here. So what we said here is that the f of x1 is the minimum value of f of x. Okay, so the f of x1 is just the minimum value of f of x. Okay, and remember that on the left hand side, f of x1, according to the definition of f, is just dx1 f2. On the right hand side, the minimum value of d of x f2 over all the x on f1 means that on the right hand side, this is equal to the distance between f1 and f2. Okay, so that's what we got up to here. And next, since we already have the x1, we can consider similar as before. We know that there exists a ball centered at x1 with the radius delta large enough so that the ball is so large that it will overlap with f2. The reason is f2 is non-empty. So when you make x1 large enough, when you make the ball centered at x1 large enough, it will overlap with f2. So the delta is we just choose delta sufficiently large so that the ball here centered at x1 will be large enough so that it will overlap the f2. Okay, and we call this intersection to be K. And remember that this is a bounded closed set. This is a closed set, so intersection is closed and bounded, and that means the K is compact. Okay, that means K is compact. Remember that we're considering this in the space of Rn. So the bounded closed set will be compact. So K is compact, and now I will define a function g. So remember that previously we have this as f1, this as f2, and then we have this x1 point here. And now I define my g function to be the distance for every x. Gx is the distance between x and x1. So for any point over the space Rn, the gx is defined in this way. And it's easy to show that the gx is also uniformly continuous. You can treat x as a set, the point x1 as a set, then this, according to the theorem before, the gx is a uniformly continuous function. And now I chose this k, I chose this ball large enough so that they overlap. So this is the ball that is large enough, and here the shaded area will be the k. Okay, and this k we show that it's compact, and the g over this compact set must attain some minimum. Let's say it attains minimum x2 here. Okay, so that means the g of x2 is equal to the minimum value of g over the k over this shaded area, and on the left hand side, the g of x2 according to the definition of g of x2 is just distance between x1 and x2. On the right hand side, the distance, the minimum distance between any points over k and x1 is just the distance between x1 and k. Okay, the distance between x1 and k. But remember that the k is chosen such that this ball centered x1 overlaps with the f2. So if the distance between k and x1 is also distance between f2 and x1. The reason is this k is actually the closer portion of f2, the portion of f2 that is closer to x1. Okay, so that's how we show that this, on the one side, it is just equal to f of d of x1, x2 according to the definition. On the right hand side, this is the d of x1 over all the x on k. So this is just the distance here, and this is just the d of k x1. Okay, so now let's see the d x1 x2 according to what we have here is just g x2, and on the right hand side is just d x1k as we just showed here, right? And dx1k is also equal to dx1 f2 because k is the portion of f2 that is closer to x1 as we draw earlier. And this, according to our definition of f, is just f of x1. And f of x1, as we showed earlier, f of x1 is just df1 f2, as we show here. Okay, just df1 x2. So that's how we show that this x1 is from f1, x2 is from f2, so that dx1 dx2 dx1 x2 is equal to the distance between f1 and f2. Okay, we start a new chapter about the measure and the measurable sets. So this is the foundation of the Lebesgue's theory. We first give the definition for sigma-algebra. Okay, so suppose that X is a non-empty set. It's a set of points, and gamma is a subset of the power set of X. So first of all, recall that 2 to the X is or denoted by px is a power set of X, means the collection of all possible subsets of X. Okay, so it's just all possible subsets of X, and the gamma is containing into power set of X, means that the gamma is just a collection of subsets of X. Okay, and we call this gamma a sigma algebra if the empty set is in gamma. So that's the first one. And if A, which is a subset of X, if A belongs to gamma, then the complement of A also belongs to gamma. That's the second condition. The last condition is that if you have countably many sets in gamma, then taking the union of them is still in gamma. So that's the last one here. Okay, so this is the this last one is very important. This is where the sigma comes from. You have a countable number of sets, and the union of them must be also in gamma. This is called sigma algebra. If without a sigma, then you can say we call gamma is an algebra if that for any finite number of ANs, each belongs to gamma, implies that the union of those finite many of the ANs belongs to gamma. And in that case, gamma is just called algebra. But what we're interested in is the sigma algebra case, where you can take the union of countably many sets in gamma, but it's still in gamma. So the gamma is closed under the union of countable sets, or countable union. Okay, it's closed under countable union. Okay, so from this definition, it is easy to derive some properties of sigma algebra. So first of all, the X must be in any sigma algebra must also contain X, the X itself. The reason is empty is in there, and for any set in gamma, the complement is also in gamma. So let's say the A is the empty set, then this is just X. Okay, so that's the first one. It's very easy to show. Second one is that let me show the first one here first. So this is that if I have countably many of them of sets in gamma, then the union of them will be in gamma. But let's say that I just have finite many of them that are non-empty. The rest are empty. Then taking the union of those things is like just taking the union of finite many of ANs, right? So in that case, this countable union in gamma implies that the finite union will be in gamma, right? If you only have finite many the case, then it will be also the union will be in gamma. Okay. So from here we can see that if I have two sets, then if A and B are both in gamma, then A union B must be in gamma as well, right? And now we can see that the A minus B will be just the A intersection of A and B complement. And that is also equal to, according to De Morgan's law, this is just equal to that. Okay, so if A and B both belong to gamma, then A complement also belong to gamma, and the union of A complement and B will belong to gamma, and this will belong to gamma, and the complement of this, which is that, will also belong to gamma. Right? That's how we show the second one here. Okay, and the last one, you will have countably many ANs, and apparently, as we showed earlier, if this is true, if we have the countable union belonging to gamma, this property, we have this property, then you see here you have we have this countably many ANs, and then I know that each of them, the complement of each of them is also in there, right? And the union of this will also be in here because, right, you have the gamma is closed under countable union, and then we apply the De Morgan's law. The complement of this is also in gamma, but the complement of this union of the complements is just the intersection of the sets, right? So that's why, that's because this is equal to this. So that's how we show that this also belongs to gamma. Okay, and similarly, you can show this. For example, the limb soup, according to our definition before, the limb soup is intersection of, say, n from 1 to infinity, and the k from n to infinity of ak. Okay, and because of the gamma is a sigma algebra, we know that this set will be in gamma, right? Because it's countable union, so it's in gamma, and then we have a countable intersection according to what we showed here. If it is also closed under countable intersection, so that's why this must be in gamma as well. And similarly, you can show this is in gamma. Okay, next let's consider the definition for generated sigma algebra. So suppose we're given a set, a collection of subsets of X. So the sigma is a subset of the power set of X. So sigma just contains some subsets of X. And the sigma itself may not be a sigma algebra, but we can use sigma to generate a sigma algebra. So this is how we generated it. Let's use this A to denote a set of the set of gamma. So the gamma is also a subset of the power set of X. So the property of gamma is that it contains the sigma. Okay, and at the meantime, the gamma itself is a sigma algebra. Okay, so now note that the sigma, the gamma, they are all family. They are all just a collection of subsets of X. But this gamma contains sigma, and the gamma itself is a sigma algebra. So A contains all the sigma algebra that contains the sigma. Okay. So now let's say that since this A contains all those kind of sigma algebra, though I can take an intersection of all those sigma algebras. So I take the intersection of all the sigma algebra, and the intersection is over all the ones in A, and then the set I get is called the sigma algebra generated by sigma. Okay, so you can check that this is indeed a sigma algebra because I leave it as exercise to you. So what you need to do is to show that this gamma of sigma has these three properties, has all these three properties. And for example, you need to show that the empty set is in the gamma of sigma, is in the sigma algebra generated by this set of sigma. Okay, and so similar to for the other two. Okay, so it's very easy to show, and I ask you to try this, practice this, and convince yourself. Okay, and the sigma algebra generated by the sigma here is also the smallest sigma algebra that contains this set. The reason is, first of all, we know that this sigma algebra, this one is a sigma algebra, as we showed earlier. And remember that since it's a sigma algebra that contains sigma, so this is also in A. Okay, so that is indeed in A. And meanwhile, it is in the intersection of all the possible gamma in A. Okay, so that means it's no larger than any other gamma in A, because this will be a subset of gamma for all the gamma in A. So that's why it is no larger than any gamma in A, and itself is in A. So that's why this is the smallest sigma algebra that contains sigma. Okay, so this is the meaning of the sigma algebra. And a common definition or common notation that you see in measure theory or in real analysis is the Boreal sigma algebra. So what this one is just you just define the sigma here to be the set of open sets in Rn. Okay, G is open, and it's just a collection of all open sets in Rn. And then the sigma algebra generated by this set is called the Borel sigma algebra. Okay, the sigma algebra generated by this set here is called the Borel sigma algebra of Rn, and this is usually denoted by the big B, the script B of Rn, or sometimes it's just a script B. Okay, in the a set in this Borel sigma algebra is called Borel set. Okay, so it's just a Boreal subset of Rn. There could be a very complicated set because of the way that we can generate the sigma algebra, but the set from there is called a Boreal set. Okay, so now let's move on to the outer measure. Okay, so this is the construction steps to obtain our measure eventually. So it is actually sourced from this outer measure. So what the outer measure, before defining outer measure, first define what is open box cover. Sometimes it's called L cover. So what that is we call a collection of countably many boxes, open boxes. So this IK is open box. So in R2, in R1 is just intervals, open intervals. In R1 it's just the open intervals. In R2 is this open boxes. Okay, each IK is one of these open boxes. Okay, it's a rectangle that does not include the boundary. Okay, in three-dimensional case, it's just actual boxes, and you can extend this to an arbitrary dimension. Okay, so if I have countably many of those IKs, that means I have, for example, in 2D, I have 1, 2, 3, 4 countably many of them, and if the union of them covers the set E, then we call this collection of open boxes an open box cover of E, or L cover of E. Okay, so now for example, if this is the E, then you can use those boxes, countably many of those boxes to cover it, then these boxes together is called an open box cover. Okay, so you can see that for a given set E, there are many ways to cover it, right? Actually, arbitrary ways to cover it. And now, for each possible cover, I can take the union of the areas of these boxes. Okay, the union or the sum of the areas of these boxes. Right? Now for each open box cover, I can find the sum of these areas, which is this. And now you can see, since we have infinitely many ways or arbitrary way to cover it, so let's see that the smallest value of this quantity here is called the outer measure. Okay, that means you can use arbitrary ones to cover it, but you can use finer cover to cover it as well. and taking the infimum of those area of those cover, that is the outer measure. So you want to cover the set E using a sequence, using a countably many open boxes, and make sure they are as small as possible. They try to make them non-overlapping and try to make them as tight as possible. So that is the outer measure. Okay, so this is the definition for outer measure. Among all the open box covers, take the sum for each open box cover. Take the sum of the areas of the box. This means the area of the box IK. So like this one, this is the area. The area just the height times the width. Okay, in 3D that's just the volume of the box. So you take this for each open cover. You take the sum of the areas, and then the smallest value that you can get for this one is called the open measure or outer measure. Okay, so this notation is this outer measure is denoted by mu star. This is very important that we'll be using this to get the actual Lebesgue measure. Okay, so there are several properties that can be easily checked. For example, for a single point in Rn, the outer measure is equal to 0. So the reason is that if you have a single point, and say I can get a box to cover it easily, right? And I can make this box arbitrarily small. And then when I take the infimum of these boxes, and I will get 0, right? So in this case, open box cover has only just one box. You can easily use one box to cover it. You can use more, but this is one way to choose it. And I can make this one smaller and smaller. Eventually, the infimum of this will be just equal to 0. That's why this is equal to 0. Okay, so not only that, the second example tells us, say, I use a very simple example here. So in R2, the set I have inside the parentheses is the x-axis, as you can see, right? The y takes the value 0. The x value is just any real number. So that's essentially just this real line in R2. And I claim that this is a this set is, so this real line has a outer measure equal to 0. Okay, so how to show this? If you look at, so let's first show that let's say I have an interval here from 0 to 1. I'll show that this interval will have a measure, outer measure 0. Okay, to show that, I can draw a box. Let's say this interval is open. It's open 0 to 1. So I can draw a very thin box, and this I will cover this interval, right? And I can make the height of this box arbitrarily small. Right? So the height of this, let's say the height is just epsilon. So this height is epsilon. So the area of this I will be just 1 times epsilon, which is equal to epsilon. And then no matter how small I make my epsilon is, this I can always cover the interval from 0 to 1. So that's why the interval 0 to 1 here just has a outer measure equal to 0. Okay, and you can make this I arbitrarily large, and it will still give you measure 0. Okay, and there's a slight glitch or slight gap here, since I have infinitely long real line here. So the question is, if I take the union of them, is still 0? And we will show this soon later. Just keep this as a question in your mind, that if I have just a finite length of interval like this, then it's easy to show that the outer measure is 0. And then we're going to use this to show the entire line has an outer measure 0 soon later. Okay. So next so keep this in mind, and we'll answer that soon later. So suppose now we're given a new theorem. So the theorem says a very trivial result. Suppose we have open box, as we showed. If we have open box, the area of this is very clear, right? It's just the volume of this, or the area of this box. And if you take the closure of this, that means you also include the boundary. The outer measure doesn't change. It's still the same area as the area of the open box. And that's very easy to show because you can imagine in this way you have open box here, okay? And although you include the boundary, which is the closure of this open box, you can still draw a very thin, tiny open box that include this closed box. Okay, and you can make this open box arbitrarily small, right? Arbitrarily small, as long as it's including this closure of I. And then you can easily show that the outer measure of this closure of I is less than or equal to the area of I plus some epsilon, and for arbitrarily small epsilon. And by that, we can show that this is just this is just equal to that. Okay, so I also want to leave this as your exercise to you because this is very easy to do, and you want to do the proof and convince yourself. Okay, so now let's move on to a more challenging one. Okay, so I'm going to show several important properties of outer measures. So suppose I have a outer measure mu star defined, be the outer measure of Rn. Then I have the following results. First, the outer measure is always non-negative. Okay, this is one. And also the empty set has outer measure equal to 0. Second one is if E1 is contained in E2, then the outer measure of E1 is less than or equal to the outer measure of E2. Okay. The third one is the so-called sub-additivity. What it says is if you take a union of you take a countable union of sets, then its outer measure is less than or equal to the sum of the outer measures of the individual ones. Okay, so this is the three properties of outer measure that we can easily get. Especially the first two are really trivial to get. So the first one, as we showed earlier, as the definition says, this is the infimum of positive numbers. So this has to be greater than or equal to 0, right? So this must be greater than or equal to 0. So the outer measure maps any subset of Rn to some non-negative number. That's very clear. And the outer measure empty set must be 0. That is also easy because no matter how small a open box cover is, it will cover empty set anyway. And you can make this open box cover arbitrarily small, and it will give you the infimum equal to 0, which is outer measure of the empty set. Okay, so this is trivial to show. If E1 is included in E2, then the outer measure of E1 is smaller than or equal to the outer measure of E2. And that is also easy to show because if you have an open box cover for E2, it must be an open box cover for E1 as well, right? Because E1 is included in E2. So you take the infimum of those open box covers for the E2, then you will get the outer measure of E2, and apparently that will be bigger than the one on the left, right? So this is trivial to show. So the most tricky one is the last one, Subadditivity. Okay, to show this, I'm just going to show you the number 3. So to show this, then I will show that for each k, or for any k, then I'm focusing on ek. For each ek, I know that there exists an open box cover which I denote by IKL, where L is in N. So this the K is for the EK, okay, is for the EK, and this IKL is the open box. And I choose this open boxes, or the open box cover, such that let me see, for any epsilon, we move this to here. So for any epsilon greater than 0 that I fix, and for any k, I can find this open box cover such that the outer measure of ek, which is the infimum of open box covers, let me just use this one. It's not difficult. It's not easy to confuse. So it's an open this is an open box cover of ek. Okay, according to definition, that's this. And because it's infimum, so that I know there exists a specific open box cover such that this is less than equal to it's bigger than, it's less than equal to it's bigger than equal to the sum of L from 1 to infinity IKL minus epsilon over 2k. Okay, so I'm going to use maybe use a different notation here as j, also j here. Okay, so what reference here doesn't really matter. I'm just showing this for this one time. In the future, I really I can just skip this because I know this is just the infimum value is the outer measure here. So because this outer measure is taken as the infimum, then I know that there exists open box cover such that it's so close to, it's bigger than, this is definitely bigger than that, but at the same time, this is bigger than equal to this minus a epsilon that I chose. But for this case, for given epsilon and k, I define my epsilon to be epsilon over 2k. Okay, so now what I get is a open box cover for the ek, whose measure, whose sum here is very close to the true infimum, which is the measure of ek, outer measure of ek. And how close it is? It is close to the outer measure of EK by at most this. Okay, that's what happens for each EK. And now I use these things to cover the EK, and for each K I have a countable many of this. So this IKL for running from all the K and L. So for each K, I know that for each given K, IK1, IK2, IK3, they together form a open box cover for EK. And then for K from 1 to infinity, 1, 2, 3, 4 to infinity, this is an open box cover of the union of EK. Okay, right? Because for each fixed K, IKL together will cover EK. And if you also allow K to vary from 1 to infinity, then these IKLs will be able to cover the union of them, union of the EKs. Okay, and because of that, I know that the mu star of the union of EK is definitely less than or equal to the sum of those IKL, where L, let me write it separately, where K is from 1 to infinity and L is from 1 to infinity, right? Because the mu star, the outer measure of this union, is the infimum of such kind of sums. So it must be less than or equal to this specific sum. And remember that for each one of them, it is less than or equal to the mu star of EK plus epsilon over 2K, 2 to the K, right? Because this is the same as what I just circled, and it is less than or equal to this plus this. Okay, so that's why I have this less than or equal to K from 1 to infinity, and mu star of EK plus epsilon over 2K. Okay, so now you can see I collected the mu star of EKs. That's what I really want on the right hand side. And I also have the sum from K to infinity of epsilon over 2K. But you know this thing is just equal to epsilon. Okay, so that's why this is just equal to the sum of this outer measures plus epsilon. Okay, and because the epsilon is arbitrary, so I know that for any epsilon, this is less than or equal to this plus epsilon, and epsilon is arbitrary. So that just means that this is less than or equal to this. Right? So that's how we got the conclusion here. Okay, so that's the subadditivity. I want to make a few remarks about the theorem here. The first one is we know that the outer measure is always greater than or equal to 0. So it's always non-negative. And we know that empty set has an outer measure 0. But there could be also non-empty sets that also have measure 0. Right? We have shown 2 examples before. For example, you have a single point, the outer measure is 0. Right? If you have just a line, then in the 2-dimensional space, the outer measure is 0. If you have a plane in the 3-dimensional space, that is also outer measure 0. Okay, so empty set is measure 0, outer measure 0, but a set is outer measure 0, has an outer measure 0, doesn't mean that it is empty set. So that's the first remark I want to make here. The second remark I want to make here is that this is called sub-additivity, means that the sum of this is greater than or equal to that. we do not have equality in general, which we hope for, but unfortunately we do not have this property for outer measures, and we're going to consider additional condition to make this equality hold. Okay, but for now we only have this sub-additivity. Okay, so this is the remarks I want to make. And by the way, if we have this, since we have the sub-additivity for infinite sets of them, for countably many sets, and it's easy to show that it's also true for finite sum. Okay, so you have this k from 1 to n, and then you have the union from 1 to n, then this still holds. The reason is you can just take all the EKs except the finite many of them as empty sets. And then the empty set has a measure 0. So when you put it on the left-hand side, this is just the union of finite many sets. And on the right-hand side, you have the sum of the outer measures of finite many sets plus a bunch of zeros, right? All the others are zeros. If you evaluate them, if you consider the outer measure of empty set, they're all zeros. Okay, so this also implies sub-additivity for finite many, for finite union of sets. Okay, so let's see an example. Suppose I have a countable set. I claim that the outer measure of E must be 0. Okay, and the proof is very easy due to the subadditivity property. We know that the outer measure of each point is 0. So, according to the subadditivity, the outer measure of E is just the outer measure of the union of this single point sets. Okay, and this is less than or equal to the sum of the outer measures for each point. But we know that this is equal to 0, so it's just the sum of zeros, and that gives us 0. Okay, and it's non-negative, so the outer measure is non-negative, and it's less than or equal to 0. Then only, and then we conclude that this has to be equal to 0. Okay, it's greater than or equal to 0, and it's equal to 0. It's less than or equal to 0, so it has to be equal to 0. Okay, so let's take a look at another example. Okay, suppose we have a set E, which is a subset of this closed interval AB on the set of real numbers, on the line of real numbers, and this set has a positive outer measure. And then we want to show that for any t between, say, 0 and the mu star of E, the outer measure of E. So since the outer measure of E is positive, so this interval actually is non-empty. So I just say that for any value between 0 and mu star of E, there exists a subset A of E such that the outer measure of A is equal to this T. Okay, so let me prove this. Okay, so let me draw the picture here. Say this is A, this is B, and the E is living inside AB. Okay, it's a collection of points inside AB. So now I'm going to define a function f is from is from R to R by, for every given x, this f of x is the mu star of the interval AX, so the half closed, half open interval, the intersection of this and E. Okay, so you can see that F is a mapping from R to R, actually from R to R plus, because the outer measure must be non-negative. Okay, and now I'm going to show that this F is a continuous function. Okay, actually not just continuous, actually it's a Lipschitz continuous function with Lipschitz constant 1. Okay, in order to show that, we need to show that. So first of all, we can show that the f of x is, the function f is non-decreasing. The reason is if you plug in a larger, x, so let's say plug in another value that is bigger than this x, then you have a bigger value here, and that means this set is bigger, and the intersection of this set is bigger than previous one, so the outer measure is also bigger, right? So it's easy to show that if x1 is less than x2, then f of x1 must be less than or equal to f of x2. Okay, so this is easy to check. Okay, and the second one is that for any delta x, so for any x and the delta x, let's say the delta x is bigger than 0, let me check the f of x, as we showed earlier, f of x must be less than or equal to f of x plus delta x, right? Because x plus delta x is on the right side of x, it's bigger than x. So this is what we just showed. But not only that, we can show that this side, this is just the mu star of ax e, right? And on the right hand side, this is the mu star of ax plus delta x take intersection with E. Okay, and now look at the set here. I can decompose it. I know that this one here is a subset of ax intersected with E union with x and x plus delta x intersect with E. It's like the distribution law, because this set here is equal to the union of ax and x plus delta x. Right? So I use the distribution law. I know that this set is actually equal to, it's just equal to this set union with this set. Okay, and because of that, I know this mu star here, the outer measure here is less than or equal to the mu star of the first set plus the mu star of the second set. All right, and this is because of the sub-additivity. Since this set is the union of these two, so the outer measure of this union is less than or equal to the sum of the individual measures. Okay, this set is the union of these two, so the outer measure of the union is less than or equal to the sum of the outer measures. So I got this, and you can see that this is equal to f of x. Okay, and that's the first term. The second term must be less than or equal to the outer measure of this, because this together is just a subset of this. So the outer measure of this set, it must be less than or equal to the outer measure of this. The outer measure of this interval is very clear. It's just delta x, right? So that's why It's just delta x. So what we have proved so far is this f of x is less than or equal to f of x plus delta x, and is less than or equal to f of x plus this delta x. Okay? So it is very easy to see that f of x plus delta x minus f of x is less than or equal to delta x. And this shows that the f is Lipschitz continuous and with Lipschitz constant 1. Okay, so f is Lipschitz, is 1 Lipschitz. Okay, so because f is 1 Lipschitz, I have a function that is 1 Lipschitz over the interval, and I know that if I check the value, say this is a, this is b, this is the x, and I know that when x is less than a, according to the definition here, if x is less than a, then this is empty set. So intersection with anything will be still empty. So when x is less than a, this is a this mu star of this empty set, which is 0. So that means when x is less than a, this is just equal to 0. Okay, and when x is bigger than b, then the interval, you have an interval AB and intersection with E, that will be just E itself, because E is a subset of interval A to B. So if x is bigger than or equal to b, this is just the E, so that f of x is just the mu star of E. Okay, let's say this is the mu star of E. It's a positive number, so this is mu star of E. So what I know about this f is that it is taking value 0 here, and it's taking value mu star of E here, and I know that it's continuous, because this is Lipschitz continuous. This is a continuous function. So that means there must be a way to, connect these two. And since it's connecting these two and it's continuous, that means for any t between 0 and mu star of E, we must be able to find some point such that its function value, say it's c. So there must be some c such that f of c equals to t. And f of c is just the mu star of the intersection of A, C, and E. So this is the subset we found. We wanted to find a subset of E, and such that the outer measure of this set is equal to T. So this is our A, the set A, the capital A. Okay, so this is by as we said, the key here is the intersection, by intermediate value theorem of continuous functions. For any t between 0 and the mu star, we must be able to find such a point C. Okay, next we give 2 results without proofs because they are very obvious. The first one is if we shift a set in Rn by some constant x, then the outer measure doesn't change. Okay, so this E, say this is the E here, and you shift it by x to a new place, and the outer measure of this new set is the same as before. Right, that's easy to show. And the second one is this only works for R. If you have a subset E in the set of real numbers, then the outer measure of a scaling of this E, so by lambda, the scaling is by lambda, you scale this, the outer measure of this scaled set is equal to the scaled outer measure. Okay, and this is the absolute value of lambda in case lambda is negative. But because if we put the negative, then it would just make a symmetric mirror of this E and then scale it. But that doesn't change the scaling effection. Okay, so this will be the same effect of the set. Okay, so the last one, I'm going to give you an example to use the property of outer measures. Suppose we have a set A which has outer measure 0, then all these three sets, A union B, B, and B minus A, they all have the same outer measure, which is equal to B. Okay, outer measure of B. Okay, so to prove this, you can see that first of all, the mu star of B is equal must be less than or equal to the mu star of A union B. Okay, the reason is because of the subadditivity. Okay, it's because of the union of A and B must contain B. So B is a subset of A union B, so the outer measure is also less than or equal to that. Okay, so now remember that the A union B can be written as the B union with A minus B, right? So let's say this is the A, this is the B. The union of A and B is equal to B, which is here, union with A minus B, which is here. So in this case, I know that it's less than or equal to the mu star of B plus the mu star of A minus B. Okay, and now note that this is a subset of A. So this will be less than or equal to, the first term doesn't change, but the second term is less than or equal to this. However, the A has a measure 0. A doesn't have to be empty, okay? But A has a measure 0, so this is equal to 0. That's why this is just mu star of B. Okay, and this shows that this is bigger than the mu star of B. On the other hand, it's also less than or equal to the mu star of B. So this one has to be equal to mu star of B. That's how we proved this. Okay, so that's the first one. The second one, we want to show the second equality. Okay, so the mu star of B minus A, on the one hand, I know that it must be less than or equal to mu star of B, because B minus A is a subset of B. Okay. On the other hand, same as before, we know that this is equal to the mu star of B minus A plus the mu star of B intersection of B and A. Okay, so this is because, again, if you have A and B, then what is B? B can be considered as the union of B minus A, which is a shaded area here, and the intersection of the two. And because of the subadditivity, I know that this must be, sorry, I should have, this is less than or equal to that. Okay? This is because B is equal to the union of B minus A and B intersection of B and A. Okay, and this is less than or equal to, so this part here, this is a subset of A. So the measure of outer measure of this set is also less than or equal to the outer measure of A, which is 0. That's why this should be just 0. Okay, and this becomes just mu star of B minus A. And but now we show that mu star of B is bigger than or equal to this, but also less than or equal to this. So that's why these two should be equal.